Sebastian, if you could just switch off your sharing screen. And yes, our next speaker will be Tailin Wu. Hello.
Hello.
Yes. So Tailin is currently a postdoc at Stanford University, working in computer science department on topics ranging from representation learning, reasoning, causal learning. And Tailin did his PhD at MIT. I've forgotten when, a couple of years ago, I assume, working with Ai Chuang and Max Tegmark. So I assume this was in physics, right?
Yes.
And then he switched now to computer science. So, I'm much looking forward to your presentation on machine learning of physics theories and its universal trade-off between accuracy and simplicity. So the screen is yours. I'm looking forward.
Okay, thank you. So today, my talk is about one equation, which is this equation, where the loss of objective is a prediction loss plus a complexity times some beta. So this equation, I think, can summarize much of the both physics and machine learning. And for example, in physics, we are trying to find some physics laws that can both precisely predict certain aspects of the world, and also is as simple as possible. This is in the principle of the Occam's razor. And at the same time, we can also think of machine learning as, for example, finding machine learning models that can both predict some target as well as constraining the model such that it has a little complexity. So for example, in many of the machine learning objectives, we have this two-turn loss, where, for example, the L1 regulation, it has the prediction loss as well as some complexity that penalize the complexity of the weights. We also have the beta VAE that both minimize the reconstruction loss as well as constraining the KL divergence between the posterior and the prior. And also we have the information bottleneck, and also many other objectives in machine learning also have this complexity plus the prediction loss. And people have found that having this complexity will help the model learn much better. So today my talk will be consisting of two parts. In the first part, I'm going to introduce our work with Max Tegmark about a paradigm to learn physics theories and to minimize these objectives of the description length of the data given the model, as well as the description length of the model. And in the second part, I'm going to introduce our study of the trade-off between these two terms, and as well as some theoretical study about its phase transitions when we tune the beta of these two terms. So in the first part, our motivating question is the following. So on the AI to physics side, we want to ask, how can machines propose theories in a similar way as physicists propose theories in order to automate this process? On the flip side, we can also ask, for example, how can we improve the interpretability and the flexibility of the neural network using insights with physics? So we start with some simple scenario in which we have some balls that are moving in some field. And basically, we can see that there may be different kind of physics laws in different regions. And the machine is not being told about what the law is, as well as about the boundary of different physics laws. But as humans, we can easily see that there are different regions. And for example, here is what the machines will see at different space. You can see that there are different physics laws. And how can machines do that? So one simple way is the following. We can just use a very big neural network and try to predict the past and to the future. This is reasonable if we only care about predicting the future. But from this, we are not able to, for example, obtain the boundary of different fixed laws, as well as it is not flexible in the sense that if we are going to, for example, encounter similar things in the future, where it is some parts of the physics laws, then we have to retrain the network again. But physics does not do this. Basically, in physics, we are trying to discover different physics laws that are only applicable to some domain. And we want that to be as precise as possible. Therefore, in this work, we propose a paradigm of learning theories, where a theory is a two-tuple consisting of a prediction function, as well as a domain classifier that classify where this theory will be applied. For example, we can develop some theories about atoms, where this theory will not be applied to anything else, but only for atoms, and so on. So, and then the learning is consisting of discovering as well as manipulating these different theories that can be applied to different domains. So overall, the whole thing is the following. So we have some environment that can continuously provide some different physics problems that may have different domains inside one environment. And then we have a differentiable divide and conquer to discover different theories in different domains. And the learned theories are collected in the theory hub. And then when the agent encounters a new environment, he should first look into the theory hub to see if any theories has been learned. And if so, it will propose new theories from the theory hub. And if some parts of the environment cannot be explained, it will initialize some new network and try to learn these theories. And the learned theories will be also added into the theory hub. In this way, the agent can continuously accumulate more and more theories. And also, it has two other things to simplify the theories using Occam's razor, as well as unification to combine some similar theories into master theories that can generate these theories by changing some parameter. And overall, this whole thing is trying to minimize an objective of the description length of the data given the model, as well as the description length of the model. So now we can look at different parts one by one. So firstly, how can we discover different physics domains where they may obey different physics laws? So suppose that we have a function f that predicts f of t, the state t, and then the target is the state at t+1. And suppose that there are different physics laws in different domains of X. So what we do is the following. We can have multiple theories where each theory are indexed by the I. And then each theory will have some laws on each data point, because some theories are better and some prediction functions are worse. And then we have generalized mean laws, which performs an average over these different theories on each data point. And then, for example, if the gamma is 1, it is just the arithmetic mean. If gamma is minus infinity, it will be the minimum of the loss from the best prediction function. And the total loss is just the sum over all the data points, where each data point is some generalized mean over the different theories. And basically, we know that from the property of this generalized mean, if the gamma is less than 0, it will basically favor or more influenced by the items that have the lowest loss. For example, that is the nearest to 0, which means that it will be dominated by the best prediction function. And we further prove that when the gamma is less than 0, and under some minor conditions, this mean will give the larger gradient for the theories with smaller loss. So basically, it means that it will try to make the better theory becomes even better if that theory can explain this part of the data very well. And if one theory cannot explain this domain very well, it will be just focused on the parts that it can explain well and gets even better. So in this way, different theories can specialize in their different region. And we also prove that it can be applied to different loss functions like MSE, MAE, and Huber loss, and so on. And then what we do to do this differentiable divide and conquer is to first train this prediction function using this loss, and then simultaneously feed the domain classifier to the best model ID as the target for each data point. And in the second stage, we will fix the domain, and then in each domain, we only train the best prediction function. And in this way, we will be able to find the best model for each domain, as well as discovering the domain boundaries. And for the second part, we apply the Occam's razor in two ways, both in the model as well as the error. So on the error side, we, instead of using the MSE loss, we use the approximation of the discussion length, which is kind of like a log of the MSE. And you can see that the loss landscape is like this, where the nearer it is to 0, the sharper it is for the gradient. And this will allow it to focus on the points that it can fit well and ignore the outliers. And then also at the same time, we also use the discussion length to find a better model by, for example, apply some greedy algorithm to simplify the network and accept it as long as it does not increase the loss, but it decrease the measure of the distribution length of the model. For the unification, we basically try to generate a master theory that can summarize collection of theories, symbolic theories, if their structure is similar, but only differ in some numerical parameters. And in lifelong learning, we just use this theory library to try to find, to store and propose theories. And for example, here is a video of learning in which the different color are different discover theory. And then the size of the dot is the description length of the different data point. As we can see, as the learning goes, basically different theories are discovered at different domains. We also see that there are some other network that discover that there are some boundary that have a different law than in the bulk. And in the end, it will discover, for example, in the bulk, it will have very, very small laws that it can barely visible. So basically, afterwards, we can discover, for example, different physics laws, like this a simple twine example in which we have like EN field, as well as gravity field and harmonic field, as well as in this double pendulum, in which there are two different domains. In one domain, the lower ball is inside the E1, and the other domain, the lower ball is inside E2, where this is much more difficult. And it also discovered the boundary between these two domains. And we also do some numerical analysis in which we compare our AI physics with a baseline, which is just a simple multi-layer network that has similar number of parameters. We also compare with a newborn in which the agent does not have the theory library, but only have to learn everything from scratch for each environment. And we can see that for the error, both newborn and the AI physics has similar like kind order of the loss, which is like 10 to the 9th more accurate than a simple baseline with MSE loss. We also discover the different domains with perfect accuracy without knowing the domain label. And it also reaches the epoch much more quickly than the other comparisons. And also with only 1% of the data, it can also reach some level of loss very quickly. So although this, for example, here is an experiment in which, for example, we first train a network, and then after training the network, we can use the collapse layer to collapse the network into some smaller network with even one layer. And then, for example, the distribution length of the model is like this. And then distribution length of the error is like this. And then we can perform some simplification by Occam's razor. And then it finds that maybe like this is a 2 instead, and so on, where it keeps the error, but reduce the model's distribution length very much. And then it simplifies into this symbolic equation. And then over many of these similar equations, it will discover by unification that this is a P1, P2, which can generate a bunch of theories. Although this framework is tested in some simple domain, it is very general in the sense that it can be applied to arbitrary number of input dimensions, as well as spatial dimensions and pastime steps, as well as the shape of the boundary and the evolution law of arbitrary complexity, because it starts with a neural network. And then we want to try to find different path domains. But it also has some limitations in which the simplification is quite limited. And also we have to provide the agent with the state variables, and it cannot deal with the raw pixels. And it's also not able to reason with concept in physics in a similar way. So after this, the Tegmark group also do some later work that address these limitations. For example, in AI Feynman, they developed this very complicated and very efficient way to do the symbolic regression that can perform this and discover the equations of some very complicated systems, like for example in this. And it's able to discover like these very complicated physics equations and with very robust to noise. And also in this work, they also discover physics laws from this distorted video. So now I would like to switch gears and discuss about the second part, which is the universal trade-off between these two 10 laws. So this kind of 210 laws, where we have one prediction loss and complexity, appears in many of the physics as well as in the machine learning scenarios. And also, one interesting thing is the following. When we tune the beta of this 10, we will see there are many interesting things happen. For example, in this work in science, the authors discovered that, for example, when we tune the trade-off between the complexity and the prediction for this equation discovery, they find that in the kinks of this figure, it corresponds to the conservation laws of the system that are important. And also, in our recent work in AI Feynman 2, we try to discover these fixed laws of the relativity. And we find that when we tune this trade-off between complexity and prediction of this operator frontier, if we limit the complexity, we will discover this Newton's law. And then if we enlarge the complexity, we can discover the actual relativity equation. And also in our work, we also find that in classification, we will also have these kinks between the entropy of the representation and the prediction and the mutual information between the target and the representation. And this corresponds to some grouping of the different class. And also in one work by DeepMind, they study the beta VIE and the trade-off when they tune the beta. And for example, in here, this blue one is the data, and then the red one is the reconstruction. And then when they tune the trade-off, they find that they correspond to some topological a difference between the reconstruction. So what are the common patterns of these different scenarios? We can see that when we tune the beta, these change are not continuous. Instead, there may be some kinks. And in these kinks, some key properties change in a very interesting way. And it may reveal some rich structures of the learning problem. And then we want to understand this even further and want to ask, when does this transition occur? For example, when does the first transition occur? and when does the subsequent phase transition occur? And then also, how does these transitions reveal the structure of the learning problem? So in here, we study in one very important objective, which is the information bottleneck. Basically, it is like following. We have some input and we have some target Y. And then we want to learn a representation that is a compressed way to represent the X. And the information bottleneck objective is trying to learn a Z that tries to occupy only the intersection part of the information between X and Y and tries to do nothing else, contain nothing else. For example, it has one objective that tries to maximize the mutual information between the target Y and the representation Z. And then it tries to, at the same time, minimize the mutual information between the representation Z and the input X. In this way, it tries to find the intersection part. And for example, the X can be an image and the Y can be a label. Also, the X can be a physical system state at time t, and then Y can be a state at t+1. And we want Z to be some bottleneck, as Sebastian said. But here, instead of constraining by the dimension, we constrain by the information content. And this is CIFAR 10, where we study in which there are different images of different classes. And what we find is that in this, when we tune the beta, there are some transition in which the accuracy will have a jump in a discontinuous way. So the first question is, when does this learn at a transition? And what we find is that at this transition, the network is able to learn a new class. For example, at the onset of learning, it is able to separate one most easy class, automobile, from the other class. And at this transition, it is able to learn frog, automobile, sheep, and truck from the other class, while the other class cannot be differentiated yet. And at this point, it is able to discover most of them. And secondly, when does the beta have the transition? So to study this, we look at the functional of the loss with respect to the representation function, which is the P of Z given X. We can think of it as this as a functional, and it will give a value at each of the representation function. And then before the transition, the Z does not contain any information about X. So we can think of it as there is a global minimum existing at this global minimum, and then this is a loss landscape. And then before the transition, the representation is independent of the X. So we have something like this. And after the transition, we can stipulate that there exists some way to go downhill so that the representation now has some information about X. So what we do is that we can expand this functional around the trivial representation up to the second order. And then we require that the condition of learning something is that there is a perturbation on the function of this, such that this curvature is negative. And through this condition, we can derive a formula, which is as long as beta is larger than this quantity, you will be able to learn something, where this quantity is a maximum correlation between the input and target. So this maximum correlation is determined or is defined by the Pearson correlation coefficient, where we allow any nonlinear function of X and nonlinear function G of Y. And then this maximum correlation is to find the Pearson correlation coefficient between an arbitrary transformation of X and Y. And the larger this maximum correlation, the smaller the beta required to learn anything. And we apply this to the CIFAR 10 dataset. And we predicted that as long as beta is larger than this, 1.0483, it is able to learn something. And our experiment finds that it is 1.048, which is a very good match. And we can generalize this technique to discover the later transition in which we can have basically what we want is that before the transition, we have a global minimum of the loss landscape. And after that, the minimum becomes a saddle point. And we require that this curvature becomes negative at the transition point. And from this, we can determine a condition for the phase transition for the information bottleneck, which is this G of the global minimum equals beta. And as long as this is satisfied, we will have a phase transition. And this will be corresponding to this formula, in which as long as beta is equal to this 1 over the maximum correlation between X and Y conditioned on Z, then we will have a phase transition. So this is a similar quantity of the previous maximum correlation, but here it is now conditioned on the representation Z. So we can understand this as an analogy with the CCA, in which in CCA, the canonical correlation analysis, in which they try to find the different linear components that are maximally correlated between X and Y. In here, this quantity is trying to find the maximal nonlinear correlation between X and Y conditioned on the current representation Z. And the different phase transition is to discover the different nonlinear component of the correlation between X and Y. And in our case of classification, it is discovering different class.
Okay, so Tailin, just to give you a time information, you have about 4 minutes until the discussion session.
Okay, thank you. So we also apply this to the CIFAR-10, and then we find these vertical lines are the predicted discovery of phase transition, and then here is the actual phase transition. And then we find that we are able to find some transition quite well. And so to summarize this section, so basically we can think of this two-term trade-off as this a different way is to minimize the precision loss constrained by some complexity. And then generally, what we do is that we have a fixed beta for the learning problem. But here we are studying the full spectrum of the beta. And then, for example, when we tune the beta, we basically tune the slope of this straight line to have a tangent line of this Pareto frontier between the prediction loss and the complexity. And then, for example, the onset of learning is at the first point on the origin, in which what is the minimal beta that is able to learn. And then when we tune the beta and decrease the slope, we are able to find different transition point. And it also has a very similar analogy in physics. In physics, we have two kinds of phase transition. One is the first order and the other is the second order. In first order, we have this different loss landscape where at one point, one minimum becomes dominant over the other, but these different minimum are far apart. And in the Pareto frontier, this will correspond to the piecewise convex of the Pareto frontier. And then when we tune the beta, we will see some jumps on these different quantities. And then in the second order phase transition, it is a different scenario in which we have some minimum, and then this minimum, after tuning the temperature, will split into some minimum around this original minimum. And this transition is second order because it is something like a spontaneous symmetry breaking. And in the Pareto frontier, we will see that it is piecewise concave, in which the slope of this Pareto frontier will change in a discontinuous way. And then when we tune the beta, we will find the slope will have a discontinuity. And we also find that in the learning problem in machine learning, this phase transition will also have some property of the critical slowdown in learning that will correspond to the critical slowdown in physics, as well as some symmetry breaking will be corresponding to the learning of new classes. And So in our case, we study one scenario in the information bottleneck, which corresponds to the second order phase transition. But in general, there are still many open problems. Like, for example, what aspect determines whether this is first order or second order in a learning problem, as well as I have a conjecture that it is fundamentally the data set that determines the frontier. And then the loss function and the model will only determine as a lens about what is the specific like details of this Pareto frontier. And then I also correspond to the yesterday's talk about from Jen's talk about, for example, I think that the hyperribbon is correspond to some Pareto frontier of this trade-off. And then we will find a good trade-off on the frontier and perhaps on the kinks of this frontier. Yeah, and then this concludes my talk. And basically, I think we want to find basically some best model that can strike a good trade-off between the complexity and the prediction. Thank you.